So thank you everyone for coming. I'm Phil Miller. I'm an independent contractor under the brand Intense Computing. This is work I did with folks at Sandia National Laboratories, who employ most of the other folks listed here. And Daisy was formerly at Sandia, now at Google. She's going to be presenting some of the pieces of this that she originally developed and some new techniques in that. Let's see. Wait, did we get that plugged in? Yes. Yeah.
The slides are online too, if you want to follow along.
Oh, yes.
You want to show the link?
Where did it? Oh, yes. The slides that I'm presenting are online at this link, and Daisy has her slides online as well. Yeah. So the motivation for this work is that we're trying to provide utility support libraries for high-performance computing applications. So in this context, that's mostly scientific simulations, engineering simulations, efforts to understand physical devices, physical phenomena through computation. So the things that we're focused on are distributed high-performance computing, so running on clusters and supercomputers, and we're focused on providing utility support libraries, essentially, for people writing those sorts of applications who need to be able to coordinate things across different processes, different nodes, with ideally as little programming effort as possible. And so in a lot of cases, our programmers are not, C++ experts. They're not often computer scientists at all. They often have a physics background, mechanical engineering, chemistry, very broad range of education backgrounds, very broad range of programming knowledge and sophistication. So we're aiming for do sophisticated C++ things, but in a way that they can handle and benefit from without having to do, a month-long training course to take them off their actual project. So we're trying to keep the syntax that they have to use very simple. We want to make it easy to integrate our code and its functionality into their applications and encapsulate what we're doing as much as possible for them. And the things they're doing have varying degrees of sophistication in the code, but there's also a lot of sophistication in the physics and in the configuration that they may want to present, both at compile time and runtime. So some features may or may not be enabled in the code, and we need to support that across a very wide range of platforms. And a lot of those platforms have not the most up-to-date compilers or runtime libraries or whatever else. So we're focused on essentially C++ 14 level functionality, because that's the baseline that we have available everywhere. And there's the potential that there are going to be multiple libraries in a single application that are all using our code, and we need to make sure that that fan-in kind of dependency pattern doesn't cause problems with usage like it can with some other sorts of libraries that may have, instance management or things like that. So with our portability demands, we kind of take an approach of living off the land, supporting a very, very broad range of compilers spanning a wide range of years of release. So old GCC back to, I think, 4 point something, maybe 4.9. Clang, Intel's ICPP, not the newer Clang LLVM-based ICPX, NVIDIA's NVCC. So we're almost at a point where every deployment target supports C++ 17, but we've been told that we still have to hold off for a few more months because, the big projects are paying the bills and they're the ones stuck on the oldest systems. So similarly, build systems, there's code using GNU Make with all sorts of crufty makefile designs. There's CMake users, some of which use very standard modern practices for that. There are also CMake users that do very weird non-standard things that we also have to support. So we kind of have to be willing and able to slot in wherever. So not quite header-only library, but there's a lot of that flavor involved. And often our users are going to be kind of importing a copy of our code into their library, embedding it somehow, and hopefully there aren't multiple copies of it across, one overall project. But we haven't encountered that yet, but we're kind of prepared for it to happen if we get more adoption. So the things that we really want to avoid as a result of all of this complication are things like interface generators, where you have to do some sort of pre-pass over the source code of the application to generate or like pre-analyze what types or what functionality is being used in the code. Oh yeah.
No, I was just wondering why. Why do you want to avoid that?
So one of the challenges with interface generators is that you have to integrate them with the build system. And if we tell prospective users, like, you can't just pound include our headers, you're also going to have to change your build process to run this extra thing in advance of building the real code, they're just going to say, nah, that sounds like too much trouble, we'll do without. So yeah, there's a lot of constraints here that we're operating under. Maybe they may be somewhat artificial. We might be able to push back on some of this, but it makes for interesting problems to solve to try to do it their way. So the other side of this is that because of the compiler portability in particular, we can't really use a lot of the quasi-reflection-ish stuff of like runtime type information or string representations of type names. Some of those compilers will give you not exactly unique names, or will truncate long template names at 32 characters or something. And so you'll end up with something that doesn't actually work. So just to give you an outline of where we're going with this, Daisy's going to talk about cute tricks for quasi-static template quasi-static registration. She'll go over how that gets implemented, some of the correctness challenges, where it goes a little bit off standard, and some use cases, and then I'll discuss a few more use cases on that. And then we'll shift gears to our library that we call Magistrate synchronization, but it actually provides somewhat more general functionality of structure recursive traversal. And we'll see how that gets applied as we go through. So with there, I'm going to hand off to Daisy.
Oh, right. Yes. And then this is. Nope. Sorry. We were close. We were close to making it simple. Okay. All right. Thanks. Thanks to the whole Dharma Quester, or whatever your team is now, for including me in this. This is really cool to see some code you wrote 5 years ago still in use, and then people making presentations about it. It is less cool when that code is like really, really cute. But I mean, some of the constraints that Phil explained maybe will give you some idea of why we have to do some of these things here, because of the ecosystem, because of the funding model they have. And so I'm going to talk through basically the general idea behind the trick that they are using. My slides are on dsh.fyi/cppNow-2022. For some reason, that color is not showing up. I don't think I have anything else in that color, so that's good. But so I have the actual tweet. I was really bad at tweeting cute tricks back when I tweeted this one. You can tell because it got 38 likes or 28 likes. And that's not as much attention as some of the other ones get more recently. But yeah, the basic idea is if you need to do something for all the specializations of a given class template, right? You need to create a list of all the specializations that are linked to a given program or something like that. Or you need to iterate over them, or you need to print out hello for each one of them because that's, what you decided to do. You can use this pattern called that I've always called the template registrar type. I've heard it called other things, but essentially boils down to template registry or automatic registry. And the basic idea is that you want to be able to use some sort of CRTP base. So CRTP, curiously recurring template pattern. There are plenty of great talks about that out there. I won't go into too much detail, but it basically mixes in some functionality and has access to the name of the type, right? And we want to be able to do something about this level of intrusiveness and have a registry of our types. We want to be able to do the same thing for templates in particular, because for types, you could just walk through and say, you could use macros or whatever and walk through and say every time you create a type, you automatically register it yourself or whatever. But here, if you're a library, you're dependent on instantiations by your users, right? You need to be able to figure out one for each instantiation by your user. So let's walk through how it works pretty briefly. So we use CRTP, right? The CRTP base has a static member that stores the result of the registration process. And there's also this, because it's in a dependent context, and if our derived type is also a dependent context, we actually have to use the inline variable to cause the constructor to happen. That's an interesting little quirk of how dependent types work in C++. But in this particular instance, in this particular infrastructure, it has to be used somewhere. Because this is kind of a minimal example, it doesn't actually get used in the framework that is, building it. You may not need that in your case. Phil,
It doesn't hurt.
Yeah, it doesn't hurt, but well, it does, because it makes your type no longer default constructable, even though the default constructor does nothing. But it mostly doesn't hurt. So this, and so because this is a static variable, and it's going to be different for each instance of this template, right? So for every time we instantiate this template with a derived, right? With a different derived, we're going to have a different static variable, right? And that means that we're going to call register type exactly that many number of times, right? Yeah, I just said we had to use it. And it's initializer, right? The thing on the right-hand side of the equal sign is going to be called at static initialization time. Now, static initialization time is a very, very fragile time in your program, and you should not do things there. If you are left with no choice, you should be very, very careful, and you should test very, very extensively, and you should not dynamically link your code. So if you're doing any of those things, like not testing or dynamically linking your code, just don't do this. Yeah?
Question. How is the register type derived default constructing resolving to a size t?
So register type, right, is a function. It's up here. And I'm going to go through the implementation of it in a second.
Oh, okay. All right.
Yeah, and it returns a size t in this case. Yeah, go ahead. Oh, I'm sorry. The question was how is register type resolving to a size t, and I answered that it's a function.
How does the completeness of derived show up here? Because when you instantiate register type, derived is not complete yet, but I think you're going to need it to be complete in order to access the member function in register type. So
that is correct.
What is getting deferred to when to make that work out?
So I gave a lightning talk on CRTP 3 years ago here that I talked about when you can assume the thing is complete and when you can assume it isn't. Basically, in this case, in order to instantiate this initializer, we don't need it to be complete. In order to invoke this initializer, we do need it to be complete. But the point at which we find out we need to invoke the initializer is in the constructor, at which point it's complete.
Aha, okay.
So there's some gymnastics going on around here, but I've definitely had people who are way better at C++ than me say, the way I do CRTP is I try to use it, find out it's not complete, and try and put it somewhere else.
That's basically my strategy. So.
Right, and it's a valid strategy. It's something I did for many years until I got so obsessed with CRTP that I actually sat down and learned all of the cases. But Yeah.
You mentioned that, well, I think Phil mentioned that the restriction is actually C++ 14 on the library. This is 17 in line.
Yeah. I don't listen to him.
Can you do without?
No.
Yes.
We can do this without. We can do this trick without. This trick could be done in 03, I believe. I mean, yes.
In line.
Yes. So you can, if you look at, so the question was, you know, can this be done in C++ 14? The answer is yes. You can. I actually have a cute trick tweet about how to do inline variables in lesser versions. So look that up on Twitter. But there's also a more production example is in ranges, which ranges v3 had to backport to C++ 14 at one point. And there are a lot of inline variables in ranges because all of the CPO's customization point objects are inline variables. And the way Eric does it is there's a workaround for it that effectively makes the same semantics happen. Because instead of using inline, you can actually make it a dependent template that's dependent on something that doesn't matter. And it ends up requiring the compiler to make it effectively inline. But the inline keyword doesn't make that simple for you. But there are a number of workarounds that are fairly well documented for this on the internet. What else am I using that's C++ 17 specific? I don't think.
Inline.
Just the inline, I think. Yeah. The infrastructure around doing that absolutely correctly is more than a cute trick, and that's probably why I stuck it in here. But it can be done. It's not too hard to do. Just copy the way someone else did it. Was there a question over here too? Oh, hey.
Oh, yeah, just for my own edification, because I don't really understand. Why are we referencing the static member variable and casting it to void in the constructor?
Okay, so the question is why are we referencing the static member variable and casting it to void? So the cast to void is to avoid an unused expression, unused result warning, which most people, you should turn that warning into an error. It should be the default, to be honest, but we can't make it the default because backwards compatibility. But the reason why we need so in the case of my class over here, right, where we actually know the entire type when we create the the base class, right? The compiler would be able to figure out that we need index. It still would not run its initializer until after the derived type is complete. But in the case of a dependent type like this, like foo, right? And somebody's going to correct me online. It may be that you actually even need it for this case. But certainly in this case, right, the compiler won't generate this thing until it knows it needs it because it's dependent. So you need a way to ensure that the compiler needs it. So actually, if you do this cute trick, or if you go to the original code of this cute trick and take this out, you'll find out that none of these things get registered, which is actually kind of funny. It shows how brittle this code is and why you should not do this. Yeah, question?
Oh, I just wanted to clarify the specific rule there is that when you have a class template, there are like detailed circumstances under which each member of that template instantiation ultimately gets instantiated. So like when you refer to registered type of derived, it doesn't automatically instantiate all of the members of that class. So like functions are not instantiated until you use them and so on. And so like you need to use the index basically in order to get the initializer run.
Yeah, and compiler behavior differs around this. I think it's starting to converge, but there are definitely compilers where this was incorrectly getting instantiated regardless. I would be surprised if the implementation in Questar, Dharma, whatever, is this simple. They've had to work around compiler bugs from all of the compilers they have to support. And they probably have to do something much more sophisticated than this in order to make all of the compilers work. There's a lot of compiler. There are a lot of compiler bugs in general around. Well, I could stop there, but there are particularly a lot of compiler bugs in general around dependent types and dependent expressions of templates, and this is a perfect example of that. Go ahead.
Just for the people that are listening online, and definitely not for me, Can you define what a dependent type is, just, for
Right, yeah.
completeness of presentation?
Somebody will correct me in the YouTube comments with the exact definition, I am sure. I can notionally define a dependent type and a dependent context as something that depends on a template parameter.
Oh, okay.
It is far more complicated than that because there are things that depend on template parameters that are not technically dependent because you're not necessarily using them. But I don't know if you've seen the contexts where you have to use type name in order to get a type name out, or where you have to use the template keyword in order to tell the compiler that something is a template.
Or this arrow.
Or this arrow, yes. Those are all dependent contexts. And that's the reason why is because the compiler can't figure out how to parse the code even without your help. Because if your type is one thing, it might work differently.
Okay.
And it might be a value instead of a type.
Okay.
Thank
you.
Yeah.
You're welcome, people online.
Kristen says you're welcome, people online. Yeah. Any other questions while we're here before we dive into how we're actually doing the registration? The main point that we've gotten to here, right, is that we are executing some arbitrary code that we want, whatever we want to do with it, in this constructor, and it's getting executed once for each type that that's derived from this, right, from this template. Yeah, and that will happen. Yeah, in this case, it will happen before main. So, yeah. C++ requires that inline variables be deduplicated across translation units. So even at static link time, the calls to this register type will be deduplicated by the compiler. If you are dynamically loading a library, you're out of luck. The standard doesn't know what that is anyway. So standard doesn't know what linking is. So, but the standard doesn't give you a whole lot of guarantees here. It's just that most compilers, the only reasonable way to implement this is to do things in a pretty well-defined order. So don't use this unless you are in a situation where you absolutely have to, and if you do, test it very, very carefully. Anyway, so let's look at the generated code. Actually, I think this is give you some idea of what I'm talking about. For like a pretty simplified version of this, where we've actually not even defined the register type. We're just going to make the compiler insert the call. And what happens is the compiler generates the symbol cxx global var init. If you're on MSVC, it's probably named something else. This is part of the ABI, I believe. Somebody can correct me. I'm sure they will. So this is all a consequence of things that the compiler is required to do by the standard, right? The compiler is required to make certain behavior happen. Here is one way that it does this. This is the compiled code from Clang, I believe. Yeah, I think it's from Clang. So the first thing we do is we're checking something called a guard variable for this thing, right? And that's because, and if you look back at my CppCon talk from last year, I talked about this a little bit about static initialization time. Static initialization is required to be done exclusively by a single thread in a thread-safe way, right? And so the first thread that reaches it basically runs this code. And this guard variable says, check if someone else has already gotten here and run this code, right? And that happens to work in multi-threaded cases or in single-threaded cases, right? If you reach the same place multiple times in single-threaded cases, you don't want to run the code multiple times, right? And it's saying, right, if we haven't initialized the thing, jump to this label, and then call this function, right? So we're basically saying, during initialization time, right, the cxx global var init is something that is called as part of the startup process that I don't know enough about to talk about well, but it's pretty well documented online, question mark. So we're actually calling the function here, right? The compiler has inserted a call to the function in this thing that gets called before main, right? We are storing the result in the static, the location of this static variable index, right? And then we're setting this guard variable so no one else does that and returning, right? So this is, to give you some idea, it is magic, okay? Like, it is magic that the standard says you have to do. And it feels like, you didn't write this code, but the compiler did because you said this, right? What happens when there's more than one? It's more or less what you'd expect. The compiler generates a init and an init.1, and I don't know exactly how that works, but I do know that those are symbols, and when you link symbols, you can't have duplicate symbols that do different things. So question of ordering, yeah. I'm not going to go into too much detail, but basically, dynamically linked libraries, be very careful about this. Especially dynamically loaded libraries, be very careful about this. This won't work like you hope it does. It is pretty easy to write a test that just iterates over all your types, serializes them, and then deserializes them and checks that they work, right? Just for sanity, don't do this if you're writing a controller for an airplane. But do think about how this works and use it to learn how static initialization works, how templates work, how dependent types work. I think there's a lot to be learned from this. And if you're in a desperate situation where your funding organization says you can't run an interface generator, you have to work with makefiles, maybe consider doing this. I don't know. Or if you're in a header-only library, or if you just want to have fun. And my next trick is for later in the talk, and so I'm going to hand back over to Phil.
You want to switch those screens?
Yes.
Quick question. You never actually showed the register type function, I don't think.
Oh, I didn't.
Oh, yeah. Question was, we never actually showed the register type function.
I'm happy to go through it real quickly, if you think that would help. Yeah, I'm sorry. I guess that slide didn't make it. So the reason why I didn't show it in the context of this trick is that the register type function is something they do.
It's kind of arbitrary.
It's kind of arbitrary, right? And he's going to talk more about their version of the register type function. In our version, we're doing something, I can go through it very quickly. We're doing something simple here where we have a registry that we're storing in a static local variable. So this is one of the ways to get around static initialization order fiasco is this will be initialized on its first use. And so you have at least the guarantee that this registry thing is initialized before this, right? Because this calls this.
Hey, Daisy?
Yeah?
The laser pointer won't show up on the video. Do you have it on screen?
Oh, yeah, I can try. I'm sorry. So, yeah. So this is one of the ways to get around static initialization order fiasco, right? Is to use static local variables like we have on line 3, right? And we at least are guaranteed that this will get initialized before index, right? So if you made both of these kind of global scope, it's entirely possible that the compiler could decide to initialize index before it even initialized this vector, and you'd get all kinds of nightmares, right? But at least because it's block local or block scope, we're guaranteed that this will happen before it's returned, right? And so all we're doing here is we're getting the registry, and we're pushing back here like a function call that inside of this function call, notice we now have access to the type, right? This is really, really powerful. We have registered something that gives us access to the type, but the thing that we registered doesn't have any of the type information in there, so we can store it in a vector, right? I guess this is kind of critical for what you're doing, basically. They're doing this basically this, but their do something is a lot more complicated. Does that answer the question?
Yes.
Wonderful. And then we're returning the index so that we can get back that do something. Right. Okay, yeah. Thank you for pointing that out. I'm sorry I missed that. Let's see if I have the ability to switch back to, that is not the right key. That is the right key. There we go. Yeah, and there's a better link there, so that should be up.
Okay. And
Oh, and your internet, sorry.
yes, there we Okay. So thank you, Daisy, for explaining the intricacies and details of that trick. I never would have been able to figure that out on my own, so I'm glad Daisy had done it before I got there. Um, or might have taken
Not actually true.
Daisy's rolling her eyes. It might have taken me a while. I'm glad I didn't have to take that time myself. So um, the places where we use this trick in our code, there's at least a half dozen of them. So we have various things I'm going to talk about later in the talk of polymorphic class serialization and reconstruction. So in that context, the things that we're storing in the registry are functions that define how to do particular serialization operations or how to get a fresh instance of the registered type when we need to deserialize it and reconstitute an issue. And we have kind of multiple different things registered there. The other things that we register are message, event, callback, whatever handlers. There are several different kinds of them. They can be class members of a target object. They can be free functions. Sometimes they're used for handling an individual message, or sometimes they're used for more weird, unusual things like scattering some data or initiating or finishing an RDMA operation. So each of those goes into kind of a separate registry instance that says, I need the RDMA completion handler registry for this type. And in all of those, we have an integer index that came with some message, and we can ask the registry, give me back the function that goes with that type. And all specifically without somewhere in the direct executable source text saying, register this type, register that type, register instantiation on int, register instantiation on double, and so on. Which in particular, in a previous system that I worked on, we found was incredibly error prone. Template instantiations in particular, people would miss making the calls to register the types they needed. So we were really keen to make registration automatic for that reason. Yes, Daisy?
RDMA.
Oh, yes. RDMA, for people who don't work in that space, is remote direct memory access, which is a way of doing communication across a network with ideally very low overhead. Sometimes it fulfills that promise, sometimes it doesn't. So other things that I mention on here, so distinguishing what the target of a given handler for a message is, whether it's an object or a free function. We don't know when the message shows up, so we need to be able to figure out what is the calling convention for the thing that we're being asked to run. That also gets registered. In a very different context, we use this for registering system components that we define, here's 20 things in our runtime that we need an instance of by the time the runtime is ready to do work for the user. We want all of those to be constructed, and they may have dependencies among them. And we don't really want to have to write out by hand which components and what order to construct them in, because that may evolve over time. So we'd rather let the compiler figure that out. So what we do is we insert those components with their dependencies in the registry. Then at startup, we say, okay, do a topological sort over all of the registered components, which may have been linked in from who knows where, so they might not have been in our source code when we wrote it. And then, based on that topological sort order, just call the initializer for each one. And other things in our system, we have kind of distributed collections of objects. So we need to be able to register those types themselves, the types used to index across those collections, the functions used to map what process a given index should be referenced to. And then also we have a notion of what I'm calling here adopted distributed types. So something that in the application code may not directly say that it's some distributed type, but we have some machinery to say, create an instance of this on every process and be able to say, send a message to the instance of this object on process 7. and our runtime will do the work to get that message to process 7 and call the right object instance with the right conventions and the right handler and so on.
Question
Yes.
about reproducibility. So I take it that you're taking the index that the linker is getting you ultimately. That's in the base class. And you're using that in packets to identify different objects. Now, when you recompile, is that going to potentially change like the way the packet's signed, since the index could change?
So the question is, in what settings can the indices generated by registration change from one run to the next? Is that a good summary? Okay, yeah. Essentially, yeah, those indexes could change pretty much at any time. They could change when we sneeze at it. We've found that at least running the same binary in comparable enough environments across a set of nodes gives us the same indices for a given parallel job. I would not necessarily rely on like differences of library version or different compiler versions, or possibly even recompilation producing the same indices. So in our checkpointing use case, we do insist on restarting with the same binary that wrote out a given checkpoint file. Oh, yeah.
Yeah, I mean, the other thing is that this whole ecosystem, you don't have two different servers running two different generations of a binary. That's not how the HPC ecosystem works. You often launch all of your binaries from one common spot on the same supercomputer. So it's often running on exactly the same hardware with exactly the same bit identical binary. So like this is not something I would do in a world where you have rolled out updates that are
Open system.
Yeah.
You can't do this at compile time because they come from different TUs, like the instantiation.
You can't do this. You can't do this sorting at compile time. Is that the question?
No. So the question is, can you do the index assignment at compile time? And I mean, if you know a way to implement a compile time counter that is standards compliant.
I have tried for years to do this. There was a trick in a bug.
21.
There was a trick in a bug in GCC 4.8.4 that caused friend injection to work slightly differently than it should, which allowed you to effectively create compile time mutable data structures. The defect report to the standard on that was, we should not allow this because this seems really arcane. If the one way to generate mutable compile time data structures was to use a friend injection bug. And basically what happened, the fix to it was to in GCC was to check for that case and just turn it off. They didn't actually fix the way hidden friends worked until a few versions later. So there was no is the answer. We need circle.
Right. Okay. So any other questions about the different ways this gets used or the horrible abuse of link and load order that this implies? The one other case that I actually really worry about breaking this, which can apply in the single binary being launched all at once across many systems, is address space layout randomization, which is a security feature that kernels and loaders and so on have embraced over time because it makes it harder to take knowledge of one instance of a server and use that to attack another one. So HPC systems probably could just do with not enabling that, but default configurations of most systems have it on, so it would have to be explicitly turned off. So I don't think that would actually bite us in a real deployment. I haven't seen it happen, but I always worry that it could come up at some point. Oh, yeah.
Yeah, ultimately, your static initializers are going to be like each file has a list, and then each compilation unit has a list, and then the linker is going to combine those into one big list of functions to call, and that is indeterminate. It will generally either be in forward or reverse order of all the compilation units you pass to the linker. But within a certain binary, that should be deterministic and not depend on address space layout.
Yeah, so the comment was that within a given binary, that order should be deterministic and not dependent on address space layout. This is, in my mind, very hypothetical of like sections per function, or, you know, someone trying to make ASLR even more capable. You know, every function should be on its own huge page of address space or something horrifying like that.
No.
Yes, and I'm seeing lots of cringes in the audience from that. Thank you.
And there's nothing stopping the compiler from deciding to do that. That's the important point.
Yeah, Daisy said there's nothing stopping the compiler or the linkers or whatever from deciding to do such a thing. So if they ever started doing it, we would have to figure out what flag to pass to ask them not to, and hope that they honor it reliably. I hope I've scared you enough with that, because now I'm going to move on to much less scary stuff, where we're doing things that, as far as I know, are all actually within the standard and not going to blow up when we, face the wrong way and, aren't looking at it. So in our particular applications, as we mentioned, are all high-performance computing, kind of single parallel job with many instances of the same binary working together, coordinating over the network to do some sort of big shared computation. So there are a few different needs for these sorts of applications that our serialization library that we've called MAGISTRATE addresses. So one of the obvious ones that I think everyone thinks of with serialization is communication. Just, when you send a message from one process to another, how do you go from, variables named in your code to bytes on the wire? Pretty straightforward. You just need, a consistent representation on each of those processes. Derived from that is checkpointing, which supports reliability. So basically, if you're running on 1,000 compute nodes in a big job, one of those nodes could crash kind of at any time because hardware has failures sometimes. And we want to be able to recover execution after that happens. So the serialization logic, it's the same thing, putting it on the wire for the network or putting it in a file on disk. You can use the exact same functionality for both. And then, you just need a way to restart the processes and load those files in and get your overall program's data structures and representations back intact so that you can resume, picking up where you left off. And another use case that we discovered for this after we'd kind of built the system and used it in a few applications was we were seeing places in our applications where memory footprint was growing, but the usual tools for detecting leaks weren't finding anything. We weren't dropping references to memory that we had allocated. Instead, we had places in the code that were just kind of accumulating memory that they kept alive that they shouldn't have for one reason or another. And the same kind of traversals that you do for serialization work just as well for asking, how much memory is this taking up? So I'll go into the details of that later in the talk. So in the network communication case, we have kind of various different issues for exactly what data needs to be transmitted. So, sometimes it's a question of like, if you have something that is a pointer or contains a pointer, do you want to dereference that pointer? Do you want to look at some particular identifier of the pointed object? And so on. Separately, you don't want to just obliviously look at every class and say, take every member one by one and just send that on, because there might be state that's transient in some fashion, an old solution value or, some sort of cache that you don't want to serialize because it's meaningless on the other end, or it's just meaningless in general if it's old data. So to do this, our serialization is kind of a two-pass approach because we're often serializing to a memory buffer. So there's a first pass that figures out the size of the data to be serialized, and then a second pass to actually pack the data into whatever buffer we've allocated for it. And then on the receiving side, there's a corresponding unpacking pass. For the resilience and fault tolerance case, basically the same usage applies. You need to know how big is the object going to be, and then how do I put the bits in place. For the memory footprinting use case, it gets a little bit more complicated because the size of an object that you might have, put into a buffer to send over the wire is not necessarily the same thing as the size of the object as it's actually taking up space in your process's memory. And again, the transient state, the caches, whatever other stuff that may exist on one process doesn't necessarily match up with what's going over the wire. And furthermore, you could actually do memory footprinting for types that you're never going to serialize. So things that you construct internally in each process that, runtime data structures, management, whatever, that you're never going to send those over the wire. You're never going to checkpoint them, but you still need to know how much memory they're taking up. So we found that it was very easy to extend our supposedly serialization library to also support a slightly different traversal pass for footprinting. So in general, if some object doesn't define its own footprinting specialization, the sizing serialization pass is good enough. It's generally going to be a decent approximation in most cases. So we'll use that and then allow for easy customization. So just to give you an example of the syntax we use for this, we tried to keep it really simple. One of the things that we inherited from an earlier system, Charm++, was that you can do this in a single method for all of the different passes in a given type. And I think, I'm trying to remember which systems do or don't do this, because we've compared to like Boost and HPX. I haven't looked at protobuf myself, so I don't know how it does it, but we can.
We do it magically.
Okay.
It's all
Yes.
magic.
Daisy says protobuf does it magically, and
You don't
I don't
write
need to worry
C++
about it.
for protobuf.
Yeah. Okay. So I will note that this is a customization point. With apologies to Inval, though, we never ever talk about it that way because that would scare our users. So we just say, if you want to support serialization, write a serialized method. Those serialization methods can be intrusive, as an actual member of a given type. They can also be free functions. This lets us write serializers for standard library containers and smart pointers. It lets us write serializers for types coming from other libraries that get used in the application. As long as we can write the code to pull out the necessary data and put it back in appropriately, we can write a serializer. So this doesn't, there can be different people writing effectively extension methods for serialization. And one other note here is that the serialize method is templated over the serializer. This is one thing this does is it actually gives us a kind of dependency separation that you don't actually need any headers for the serializer visible or the serialization class visible where you write this code, because that can all get instantiated later. And that also means that you can do, so in the earlier Charm++ system, that was actually a virtual class with particular methods, which constrained adding functionality later. Did I see a hand raised? No.
You must have a deserialized function that's different from this.
No. The question was, you must have a deserialized function that's different from this. The answer is, no, we don't. This does sizing, packing, unpacking. This is a structure recursive traversal. It tells you which members you need to do something to. It can go both directions on them.
Depending on the mode of the serialization, it knows whether it's reading or writing or checking.
Yeah, so what's going on is that the instantiation of serializer determines whether you're loading data into the members or loading data out of the members or writing data back into the members from whatever buffer, file, whatever. So we have a sizing serializer, we have a packing serializer, we have an unpacking serializer, and so on. Does that make sense?
There's a very critical design point here. This is the right way to do this, and I will fight you on that. When you have something that is this fragile and this brittle and order dependent, and you need it to be in the same order in two different places, don't make your user write it once. Make your user write a template and pass it different things each time, right? Because it is so easy. When things are the same, make them the same in code. This is a very important design point that I think people don't think hard enough about. They're like, well, I'd rather avoid templates because that's too complicated or something like that. I know no one in this room, but someone out on YouTube is like, well, we could have a serialize and a deserialize, and then we wouldn't have to have a template.
So if you have a std vector in there, like you have to stream out the length first and then the data. So how do you?
So the serialized function, or
Yeah.
so the question was, if you have a std vector in there, how do you deal with the length and the contents and so on? So the serialized function, so it recursively calls the serialized functions for each type reference.
Partial for vectors or something. You can't do it.
Yes, well, we have a specialization for vector and overload. Sorry, mixing up overloads and specializations. But at any rate, so that bar operator basically gets to internal machinery that gets to dispatch logic that figures out, are we calling an intrusive method? Are we calling a free function? Are we calling, just memcopy, whatever we're doing there? But at the site where you write a given serializer, you don't want to have to think about how is the serializer for each of those things I'm serializing implemented. You just want to ask the library, find the serializer for this type, call it on this object, and call it with the instantiation of the serializer that I'm being instantiated on myself. Yes.
Let me clarify a little further. For this is the general version for when you are deserializing something that has a constructor you have to call, like vector. You're gonna say if s.isUnpacking, call the constructor.
Yeah, and we'll see that. We'll see that in a minute. So just we'll see the reconstruction in a moment. So here's a sketch of the concept for a serializer that you could pass to an instantiation of that method. So there's the sizing, packing, and unpacking, and I think I probably can't really highlight that well. But yeah, there's sizing, packing, and unpacking flags. Okay. So that's how those methods. Here, I got that. Yeah. So those are flags that let a serializer that needs to do something more than trivial ask, what direction is this serializer going?
Is this a global thing in a configuration or command line argument that's going in?
Is what?
Figure out if you're unpacking?
Oh, no. So the question is this a global thing or some sort of configuration for going in or out? No, this is entirely runtime. In any given... So when you send a message, the runtime system is going to pass a sizing serializer to do a traversal to figure out how big the message is going to be. It's going to allocate that, and then it's going to call a packing serializer to move the data into the message. And then on the receiving side, it's going to call...
But these look like global functions.
Oh yeah, no, this is methods in the struct serializer implementation.
Okay.
Sorry, I had in an earlier version of the slide, I put struct serializer with curly braces around all of this. I just kind of elided it for
I thought
space.
This was main, like a
No. This is not global. This is, oh, yeah, sorry. The comments I put in there were a little confusing. Yes, this is just the main methods that you're likely to see called in a given serializer, or in a given serialized method, I should say,
Okay.
that the client code will think about. So the actual working bits on here are these two methods, contiguous typed and contiguous bytes. So that basically tells whatever serializer type, here are, raw objects that I potentially want, take an array of them, or here is, a primitive type, take, its size of, and put it in the new buffer.
This isn't special syntax, it's a typo.
Wait, what was the?
Type name.
Oh, oops. Yes, that was just a mistake.
What
Thank you.
requires.
No, that's special syntax.
Yeah,
That's real,
the
unfortunately.
double type name there is just a mistake on my part. Pretend there's only one of that. And then to support the footprinting functionality that I described, we also again have a mode flag method to ask, is this footprinting? And we added methods for counting some number of bytes that might not otherwise appear in the serialization, or just saying, I know there's another n bytes that exist in my memory footprint, add that to the count. And finally, so we support a static dynamic combined analysis for sanitizing these serializers, for essentially checking, did every member get handled? Because that's another common error mode for users, to add a new member to a class and then forget to add it to the serializer. Yes?
When serializing, do you put alignment in it, or is packed?
So the question is, when serializing, do we align the data or pack it? In our case, it's all packed, where, if there's padding or something in the object, we're smashing that out, because we want it to have, in the cases that we work with, we want it to have the smallest on the wire representation. But it would be very easy to have, something that preserved alignment so that you could transfer something directly from memory to memory and access it directly or something like that. So that would be possible to customize. Again, because those serializers are templated over exactly what kind of serialization you're doing. Thank you. So the other major customization point in our serialization logic is reconstruction. So if you have something that's more complicated than a primitive type, or plain old data struct, maybe aggregates, whatever, and you actually need a constructor to run, we have a few different ways of expressing that. Again, potentially intrusive, potentially extension. So the first way is, if you define a constructor that takes a tag type from our library, it's essentially as simple as a default constructor, but it might avoid allocating or initializing things that it knows are immediately going to be overwritten by deserialization. So it can potentially save overhead relative to default construction. Another way is you could have a member reconstruct function that it will be handed a void pointer buffer, and we want it to effectively do the equivalent of in-place new in that buffer. But what constructor it calls and what arguments it passes can all be private functionality encapsulated in the class. So if it needs to, if it wants to call some particular constructor, I guess you could do a forwarding constructor from the tagged thing as well. But that, yeah, we wanted two different options there.
I should be clear, this is the reconstruction of the object prior to calling deserialization.
Oh, yes, thank you. Yes. So again, for the sake of allowing for extension method kind of designs, interoperability with libraries that don't have serializers themselves, you can define a free function, reconstruct for whatever type. And what this is going to do is it's actually going to allocate into, here I'm actually going to point at the screen. So this is a little unusual. We're taking a reference to a pointer. So it's going to be passed some local variable that's initialized to null. It's going to be expected to allocate a my class, assign the pointer into that argument, and construct it in. I might be messing up my arguments there.
No, that's correct.
In that buffer.
Is the buff the serialized data?
The question is the buff the serialized data? No, it's not in this case, because only the serializer itself. That's why I think it might be that it's supposed to do in place new in that buffer and then assign the pointer out, but I'm misremembering something at this point. Or I messed up in copying the signature onto my slides.
And the member reconstruct is a static member?
Yes. The question is the member reconstruct a static member? And yes, by necessity. And then the last option, if there's no customization, is we'll try to call a default constructor. And if none of these are defined and you try to unpack something, then it's just going to not compile because it's missing a way to do that reconstruction. So here are some examples. The progression here is maybe not ideal, but so if we have a simple type foo with an a and b ints and then some cache of something or other, and we want to write the serialize method for it, we're always going to serialize a and b, but we only ever want to look at c, that cache that doesn't need to go across the network or be saved to disk or whatever, if we're in the footprinting case. So we ask the serializer, are you a footprinting serializer? And only in that case do we then recurse into the cache and traverse the contents of the cache for serialization purposes. So the other example on here, which is, I think, pretty much the most complicated serializer we have written in general, is for std unique pointer. And this shows pretty much everything all at once that the library does. So first of all, if we're in a footprinting mode, then we tell the serializer, count how many bytes the unique pointer itself takes up. Because suppose you had a vector of 100 million unique pointers that were all null. You would still need to say the footprint is 100 million times however big unique pointer is. But if your serialization of that vector just said serialize each object and it was just going to come back with, oh, yeah, it's all null, you just reduced your apparent footprint by a factor of 8 or something for that single Boolean is null flag. So we needed to be sensitive to that. So then the actual serialization logic for a pointer, we first assign a flag of whether or not it's null. And so what's going on here is that in the packing case, we assign and initialize this variable. So we look at the pointer and say, is it null or not? And we're relying on the fact that default construction is going to be null initialized. Then we serialize that flag. And we look at the flag in all of the cases, particularly in the unpacking case. Maybe what we were asked to unpack into might not be null because we do support in-place deserialization. So an application can initialize its structures and then say, okay, now deserialize from a checkpoint, and it'll overwrite that. But otherwise, if we're in other cases of sizing or packing, if it's null, we have nothing more to do. Is there a question?
Yeah, you said there. Oh, no, I see.
Okay, there was not a question.
Reparsed it in my head.
Okay, so going from there, if we're not in the null case, if there's actually an object being pointed to, then we ask for the pointer to the object, so just calling the get method. There's a whole lot of machinery to basically do dispatch to the reconstruction logic through potentially customization points in the library, saying, if we're doing that, do that reconstruction into this pointer, which might be null coming in, but is not null coming out. Then we do, oh yeah, and it's important to note, when we're in the unpacking case, we've gotten the value of the isNull flag out of the serializer here. So whatever, so even if the pointer that we're unpacking into was not initialized, we're not relying on that to say, okay, we are actually coming up with a new instance of the object. And so then finally, if we're unpacking, then we reset the pointer to whatever we reconstructed. So again, right, supporting the case where the application reinitialized stuff and then said, okay, load from a checkpoint after that. And then finally, the very end, serialize the actual pointed to object. Yes, Chris.
I think we talked about this before, just to throw some extra confusion in here. When you do the get pointer, that can actually be a derived type of your pointer. So you're actually reinstantiating not the type that you're pointing at, but a further derived.
Yeah, so the remark was that do we handle polymorphic classes here? The answer is yes, we support polymorphic classes. I'll discuss that in a minute. Is there some note? Yeah, okay. So yeah, that's actually, wait, did I go out of order there?
You just forgot to highlight my...
Yes, okay, yes. I was gonna hand off to Daisy briefly for a cute trick for automatically generating serializers for aggregates. I think I described that correctly. Here we go.
Yes. Okay, I am so unreasonably excited about this. I have been, yes, I tweeted this yesterday. You can't obviously read it there, but I'm gonna do a slightly simplified version of it, I think. So basically, yeah. So C++ doesn't have much reflection. Hopefully we will soon, but even super simple things like counting the number of data members in a type can't be done generally. We can count the number of data members in an aggregate with this trick. And I think it's used several places. This is not original to me, although I may have come up with it independently at some point. But there's certainly a number of other places that it's used. A number of people have come up with it independently. And this is the simplified version. I don't have perfect forwarding in here. But the basic end goal here is this. We want to be able to say, for some arbitrary type, we want to static assert that the number of members is 2, or that there's the size of the aggregate is some given number, right? So we want to be able to construct a concept like that. So I'm going to walk through this in a second, or now. So the way I stated the trick here is that you can figure out how many members are in an aggregate by trying to construct it with objects that are convertible to anything. I'm going to break down what all of those things mean, and I'm going to try and go a little quickly, but I am unreasonably excited about this. So, objects convertible to anything. Well, C++ provides a conversion operator, and we can template that. So this object is not quite convertible to anything. It's convertible to anything by value. I'll go through. This is the more complete version, right? This type is convertible to actually anything, right? If you use it as an argument to a function, or as an argument to a function, or as an argument to a constructor, it will work, right? This will deduce anything. Try constructing it. So we need to be able to do something like this. And I'm using C++20 notation because we're all here because we love C++20 and at least wish we could be using it. But you can do this in Sphene. It's just much harder and much uglier. You can backport this all the way to this part of the trick. You can backport all the way to 11. You do need parameter packs. I guess you could write out all the possibilities. So you can backport it to however far you want to masochistically do so. But we need some sort of magic to do this repeat in times, right? I've kind of hand waved at it here. So what's a way to repeat something in times? So in C++20, there's a pretty compact way to do this. And I talk about this some in my CppCon talk in more detail than I have time for here. But one way to do this in C++20 is you can give explicit template parameters to a lambda, right? And so then when you deduce this std make index sequence, you'll get a parameter pack that is going to be of length n, right? So we now have like a context to do things in where we have a parameter pack of length n, which is actually useful. I'm going to show you how we're going to use that in a second. In older versions of C++, you have to do this with a separate function call. You can't do it in a lambda, but it works essentially the same way. And now, because we're in a concept definition, right, where we're trying to do something, we actually instead want to do something in this context, not inside the body, right? So one thing you may not know unless you've ever tried it before, which why would you have? But if you have, you would have found out something very surprising, and that is that anything inside the body of a lambda in a concept is not Svine safe. It's not, if it's invalid, then compilation just fails. So we can't check for something inside here. We need to actually check for something working inside here.
So you're constraining the lambda?
We are constraining the lambda, right? And then the overall concept, right, is going to check whether that lambda is valid to call, which will only be valid if you, right. Because this is an expression of calling a lambda, right? And that lambda is valid if its requires clause is valid, because there's only one overload of it. And so that all works. This is a trick, a little trick that many of you have probably seen before. If you want to repeat a type multiple times for each element of a parameter pack or something like that, you can make this kind of cheesy alias template, right? And we can just stick it in here, right? And so now we say requires, and try to construct the type with a repeated with any on the anything that we talked about last slide, right? So we've constructed now in any's, and if t is constructible with in things, right? Then any will be castable to them because it has an unconstrained template cast operator. It will be castable to the things that call is, right? And this will be a valid expression. The requires clause will return true. And then this lambda will be callable, and then the broader requires clause will return true because of that, and everything will work. And so we have found out a way to figure out if we can call the constructor of a type within things, right? That still doesn't, we need one more step here, right? We actually need to say, first of all, this only really works if it's an aggregate, right? If you have user-defined constructors, then this doesn't really tell us anything about the number of members, right? It's constructible within things, but it also has to be not constructible with n+1 things, because if you tried to construct it within things, some of the rest could get filled in with defaults, right? Because of the way aggregate initialization works. There are fantastic talks about aggregate initialization. I recommend bugging Teamer because he's great with it. Or Barry Revson on Twitter. Either of them are great. They know way more about it than me. There are some details I left out. If you look back at the original tweet, go into the slides. I posted an advanced version. If you actually want to use this in a real code base, the advanced version has some details in it that you should be doing. Like, for instance, you have to do special things in this constructor to make sure you don't accidentally pick up a copy constructor. And there's some other little things I did, like instead of using repeated with, I just stuck this index in a template parameter of the any and a few other things. but yeah, I'm not going to go into that too much. The interesting question is, what can we use this for? And there's one more step before we're actually going to tie this back into something that is going to look really, really cool in the context of this serialization talk. So we have a concept now that tells us the number of members in an aggregate, right? We can create overloads, and then in these overloads, try and destructure our aggregate, right? And now we have the types and the values of all the members, right? Because this is aggregates allow for destructuring, right? Through structured bindings, right? So this, I've omitted perfect forwarding for brevity. It's not trivial. It's actually pretty difficult here. You have to do something analogous to std forward as tuple and do all kinds of other things that are a mess. Because structured bindings are much more of a mess than you think they are. And you can't spine on this, right? You can't try to do this and then hope it succeeds, because structured bindings are always only present in a statement, not in an expression. And you can only spine on expressions. You can only do concepts that work for expressions, right? So if you try to put a structured binding that's invalid inside of a concept, your program will just fail to compile, which is correct behavior, right? You're not allowed to put statements inside concepts, which is not something anyone really realizes until you try and do it on accident. And that's because most things in C++ are expressions. There's only a few things that are exclusively statements. And structured bindings are one of them. So you have to do this thing that you used to have to do in C++ 03 with variadics, where you say, all right, I'm just going to create overloads that do the same thing for all of the cases I care about. If you're writing a library that a bunch of people use, it's not hard to go up to like 32 and say, if you're larger than 32, then you have to write your own serializer. Or you should probably write better code that doesn't have that many data members in an aggregate. Yeah, so I explained the structured bindings, but here's the cool thing here is we can automatically write serialization and deserialization functions with this, right? We can do that serialized template based on this, right? So I have this callback. That callback can be the serialized inside of the generated serialized template, and it now knows about all of the members of your aggregate. It can call serialize on them recursively, and we're done. The user doesn't have to do anything. This does require 17. Be careful with it, like anything. If someone's using an aggregate a way they shouldn't be using an aggregate, then I should also point out that you can destructure things that aren't aggregates. In theory, don't, because you're probably violating something that the user didn't think you could do. But yeah, that's this trick, and that's kind of a next steps type thing that can be done in this space where you have automatic registration. You can actually, in many cases, and as the committee gives us more and more reflection features, we will do more and more of this. But we make do with what we have for now, and this is one of the things we have that you may not realize is a reflection feature of C++.
For the aggregate copying out here, does that only work if you have public members? If there any of them are private, are they hidden then, or are you screwed?
Unfortunately, no. So the question is, does this only work if you have private members?
Only the public, but not.
Oh, does this only work if you only have public members? Unfortunately, no. So be careful. Although I'm not sure how you're constructing an aggregate that's composed only of private members, because if the moment you have a constructor, right, it's no longer an aggregate. User-defined constructor, it's no longer an aggregate. But you can actually destructure things with user-defined constructors, which is kind of a problem.
Also, in order to be an aggregate, it has to have only public data members.
It has to have only data members of the same access.
I think there's an aggregate versus standard layout distinction.
Yeah, it's okay. You're right. You may be correct on that. That's true. You're right. That may be standard layout. We should continue, though.
A quick question. The slide deck online ends at the title of the slide. Like the guts of it aren't present. Are you going to update it?
It should be updated. Try doing like a hard refresh. It may be cached incorrectly. I did upload this. We are actually running this from the internet, so. Or like a force refresh or something. Kristen?
Okay, so you can't spine inside a lambda, so you need a sub requires clause. I get that. Why do you need two requires keywords?
Because C++ loves keywords. And we love using keywords that mean different things. So C++,
Can I suggest just defer to the internet for that one?
defer to the internet, yeah, because there's a few things we want to get to still.
Okay,
but the first one, yeah.
Double requires is discuss.
The first one means one thing, the second one means a different thing.
Okay.
Because that makes sense.
Okay. Okay. So we'll switch this back. Go. Okay, cool. So thank you, Daisy. We have not yet implemented that trick for automatically generating serializers for aggregates. Besides the reliance on C++ 17, it's also just new enough that we haven't had the opportunity yet. This kind of came up in preparing the presentation. So we'll move on from there. So as has kind of been alluded to earlier in the talk, our serialization library supports polymorphic class hierarchies. So in general, it's kind of difficult to do serialization of these hierarchies. And the manual implementation is empirically very error prone. I've seen people find a dozen different ways to screw it up and not notice. It makes for extraordinarily hard to debug problems. So we really like to avoid it. Oh, I get my notes if possible.
Yeah.
Yeah. Yeah. I feel like there are things I wanted to remind myself of here. So usage of this is mostly in the checkpointing use case because what exact instances of classes you have is configuration or command line argument dependent more than it is, data dependent. So this is something that reflection would potentially facilitate. This is something that, in theory, runtime type information might help with, but for all sorts of reasons, we really don't want to use runtime type information. It's not reliable across compilers. Our environment sometimes might want it disabled, et cetera, et cetera. But the important point here is that concrete types need to be stored or sent across the wire for reconstruction. We need to know what the concrete type is on the receiving or loading end to reconstruct the right type that we're then going to deserialize into. And having written the code for doing that manually, a switch over the type identifier, and then, case this new type 1, case 2, new type 2, et cetera, really terrible. Also doesn't support extension, composition very well. If you link in different features, your reconstruction switch also needs to account for which classes you actually have available. So we rely heavily on the registration for this. So the registration pattern that we discussed earlier gives you a unique integer for each type. Using CRTP, or actually the syntax I'll show is a macro because our users don't like CRTP.
They're wrong.
Daisy says they're wrong. I don't disagree. So basically, we insert some special implementations of library-specific virtual methods that handle walking up the inheritance hierarchy from the most derived type all the way back up to the base. So it's class hierarchy recursive now. And because each class's serialized method is a template, the registration that we do is actually an instantiation of that serialized method template for each of the serializers that we intend to call. So the registry will then give us, at the point of deserialization, we ask it for, how do I reconstruct this object? And then we ask it for, okay, how do I deserialize this object? Because we also don't directly have, you can't say virtual on the serialized method because it's a template. So something has to encapsulate that. So just to illustrate, a simple usage of this, we have our base class here. It has the macro version saying this is a root of an inheritance hierarchy tree. It has its own serialized method that just handles its own types. Then we have a couple of derived types, B and C, that each say they're derived from A. Their serializers make no mention of the base type or any intermediate derivation. They just say serialize my own members in both cases. And then our type D has a unique pointer to an A, the base type. And our default constructor will say, it makes an instance of C. The serializer just says, pass that unique pointer into the serialization machinery, and it knows how to do all of the serialization, reconstruction, deserialization, et cetera, based on that. Yeah.
Do you have shared pointer?
We do not support shared pointer because it largely doesn't exist in our use case. We don't really have cross-linked references that come up, so we just don't handle that. In part because we don't want the complexity, overhead, whatever, of like thunking off the pointers and keeping track, object identity, and so on. So no, we don't have shared pointer or whatnot currently. Which is something that Boost, for instance, does handle, if I remember correctly. So just a little bit of comparison to related designs, and there's one more point I want to get to in the last 2 minutes. I'll go through this quick. So I mentioned earlier, Charm++'s pup takes a reference to a concrete serializer base type. So it has dependencies on the actual serialization library. The reconstruction is not customizable. Polymorphic types requires explicit registration, and the base class serialization requires an interface generator and a few other things that we wanted to avoid. Boost, you can either explicitly register classes, or you can use stuff that relies on type ID or user-specified strings. Again, things we wanted to avoid. In the case where you have, potentially combinatorial sets of template instantiations, dimension, cross geometry, cross numerical method, cross whatever, those strings can get really, really huge. And so we don't want string identification anywhere. Our debug symbols are bad enough. So I'm not too familiar with protobuf, which I feel a little weird saying because it's so ubiquitous, but I am familiar with the fact that it requires some sort of pre-processing pass to generate the serialization logic. And in our case, we wanted to avoid that. So I'm briefly going to mention that we have implemented a design for sanitizers that you can compile your code with the sanitizer. It will generate kind of a parallel set of checks that just enumerates all of the members of a class, and then you run your tests of the serializers to get coverage of the actual serializers, and then it will do I'm just going to skim through very quickly. It will do a set difference of what members were there in the class itself versus what members were named in the serialization, and tell you if something was missing. So we've used this to detect a couple of bugs in our runtime itself and a few more in the application. And this helps immensely for maintainability of serialization routines because you no longer have the potential for mismatch. Okay, and the last thing that I'm going to note is that because we're doing this structure recursive traversal of arbitrary types, you can do pretty much whatever you want that needs that kind of structure recursive traversal. So you define something that implements the serializer concept. If you need to do something between individual serialization calls, or when you go down or up levels of recursion, you can add a dispatcher that handles that. So our serialization sanitizer checks at each level what has happened. And then you just call traverse from our library. You hand it the serializer, you hand it the target object, it will call your thing on all of the members recursively of whatever object you handed it. So the sanitizer is a traversal. The footprinting is, a traversal outside the normal serialization logic and so on. And you could also do, besides, I mentioned on the slide, RDMA, remote direct memory access. So you could, where you have big arrays, just leave a pointer and say on deserialization, get the data from here when you're ready for it. You could also stick in compression of some sort and so on. So yeah, I will end there. Thank you.